All right, so welcome back. This is now going to be section 9.2, and we're still going to hypothesis test, but now it is going to be two samples, and rather than their proportions that we're going to compare, we're going to compare the means of these. Okay. Now, there are two types of two-mean hypothesis testing. In this session, we're going to take a look at independent samples. That is the idea that these two samples are from different populations, group 1 and group 2 kind of thing. Okay? So we are going to have sample data from two independent samples to test the hypothesis made about those two population means. Okay. We're doing independent ones in this section. There are dependent tests about two means. That's section 9.3. Okay? So we'll worry about those match pairs in the next section. In this section, we have one objective. That is just to do our hypothesis test, to conduct a hypothesis test about two independent population means. Again, since there's two groups, there's a whole bunch of data floating around with sub 1s and sub 2s. Sub 1s, right? That's all information about group 1. A mu sub 1 is a population mean. An x bar sub 1 is a sample mean. If we have a sigma sub 1, that is a population standard deviation. I'm not sure why it says mean right there. That should say standard deviation. I'll make sure I make a correction and put it in your notes. If you have an S sub 1, that is sample 1 standard deviation, and our N sub 1 is sample 1 size. Correspondingly, there's all the 2's. Population mean 2, sample mean 2, population 2, population standard deviation, sample 2 standard deviation, and sample size 2. Okay? Our hypothesis testing is going to have all those things floating around in it. Claims are going to be made about these guys. Data is going to be collected here, and that data will be used to test the claim. To test claim. Okay. The requirements are, well, first off, these two, if we know them or if we don't know them, doesn't matter, but we don't assume that they're the same. We don't assume that they are the same value. Right? So if we know them, we can show they're the same value. If they're unknown, we just assume, or we must have some reason to believe they're not the same. The two samples are independent. Again, this idea that the group that I talked to for sample 1, the group that I talked to for sample 2 are not connected in any way. The answers from group 1 don't apply to group 2 and all that. Of course, simple random samples, that's an always thing, right? And then the last one, when we talk about large enough, we say that the two sample sizes are both large enough. That is, they're both bigger than 30, or both samples come with populations having normal distributions, right? Now, the math behind the scenes. The math behind the scenes is to take two data sets and turn them into one data set. The way that we take two data sets and we turn them into one data set is we take a look at either turning them into a t-score or a z-score, depending on what kind of standard deviations we know. If we know sample standard deviations, just like with one sample mean testing, hypothesis testing for the mean, we use t's. If we have population standard deviation, we do z's. Okay, so again, over here on the left, this is if we have sample standard deviations, the realistic, the honest scenario. Over here on the right, this is the weird, the odd, the non-standard case where we somehow know population standard deviations, but we don't know population means, which honestly rarely ever makes any sense. So yes, it can be done, but realistically, we live here. Sample data, sample standard deviations, The math behind the scenes is to place all this information on a t distribution or the student distribution and run the test that way. Okay? Let's take a look at what this looks like and see if we can make some sense of it. Okay? A credit card watchdog group claims that there is a difference between the mean credit card debts of households in California and Florida. Okay? So right there, that is our claim, but it also defines our two groups. One of our groups is people from California, and the other group is people from Florida. Now, since I'm going to go with my standard here, California is mentioned first, I'm going to call that group 1, and I'm going to call Florida group 2. Okay. The results of a random survey of 250 households from each state are that X bar 1 is that, X 1 is that, X bar 2 is that, and sub 2 is that. All right. The two samples are said to be independent. That is that group 1 California and group 2 Texas, there you go. I'm sorry, Florida. Why am I saying Texas? I don't know. Florida are independent. And here's something weird. We're supposed to assume that the population standard deviations are known for both Florida and California. Now, I want to point out something else here. In this statement, do you see how they're defining group 1 to be California and group 2 to be Florida? So we don't really even have a choice. Even though I thought I had a choice when I did this, later I realized I don't have a choice. Okay? All right, so let's take a look at the claim. What is the claim? Well, the claim is that there is a difference. Now, this is a weird one. A claim of a difference doesn't tell me which one's bigger, just says they're not the same. That is that the mean debt from group 1 is not the same, different than the mean debt from group 2. That's all the different means. All right? Let's turn that into a pair of hypotheses. All right, so I need a null hypothesis and an alternate. Since my claim is a statement of not equal to, that's going to be the alternate that the mean from group 1 is not the same as the mean from group 2, which means that my null is that the means are the same. That the average credit card debt in California is the same as the average credit card debt in Florida. Our claim is the alternate. I'll need that for when I get my final results. Right? Now let's take a look at the data. I've got a lot of data here. I've got that X bar 1 is 3060. I've got that N1 is 250. And I've got that sigma 1 is 960. I also have that X bar 2, the sample mean from group 2, is 2910. I've got that N sub 2 is 250. And I've got that the population standard deviation is 845 for group 2. Right? I'm going to write that nicer. That's kind of ugly. 845. That didn't get much nicer. A little nicer. Okay. Now I need to run the test. But because the data determines the test, because more importantly, the standard deviation determines the test, and since the standard deviations that we have are population standard deviations, that means I need to run a z-test. Specifically, those two things right there tell me that I'm running a 2-sample z-test. So over to my calculator, to stat, over to test, 2-sample z-test. I punch that up, and it's going to ask me for a bunch of information. But before it gets to that, I want to point out that this is just like with one sample. If you have the stats, you can type them in. But if you had data, raw data, you could type that raw data in too, and the calculator would like it. It would just want to know, where did you put the data? So see how list 1s and list 2s show up? Okay? But we have statistics, so I'm going to put that in. Now, the order that they ask for these things is kind of wonky, so pay attention. It wants standard deviations first. So for whatever reason, 960 and then 845. And then it wants sample 1 data. So X bar was 3060. N sub 250. X bar sub 2 is 2910. N sub 2, 250. And see that down arrow over there on the left? That means there's more. So I actually have to scroll down because I needed to tell it what kind of hypothesis test. So the alternate is a not equal to. So essentially we're running a two-tailed test. So I'll select that and then I'll ask it to calculate. If I needed the standard test statistic, there it is. It's 1.854. Okay. But what I really need is my p-value. So I've got a p-value here from the problem. The test ran and said that, hey, this data gives you a p-value of 0.06. Oops, I forgot. I never wrote it down in my data. What was my alpha? Well, luckily it's in the problem. It's right there, 0.05. So when I compare p to alpha, p is greater than alpha. Greater than alpha means we fail to reject that null hypothesis. Since we are failing to reject the null hypothesis, and our claim was the alternate, then we say that there is not enough evidence to support the claim. Or there is not enough evidence to support the claim that, what was the claim? Oh, the claims that they were different, that the means are different. And again, like every time, you could fluff that up as much as you want. You could be, there is not enough evidence to support the claim that the mean credit card debt of California is different from the mean credit card debt of Florida at a significance level of 0.05. Right? I'm just going with the minimum that I need to convey the proper information. I'm not supporting it, and I'm defining what the claim is. Okay? All right, so I want to back up and point out something. Problem gave me population standard deviations. That's why I ran a z-test. Take a look at number 2 here, or our second example. The results of a state mathematics test for random samples of students taught by 2 different teachers at the same school are shown below. Can you conclude that there is a difference in the mean mathematics test score for the 2 teachers at a significance level of 0.10? Assume the populations are normally distributed and the population variances are not equal. Well, let's look at the data. Do you see how here for teacher 1, the data that we have includes a sample standard deviation? And over here for group 2, the data that we have also includes a sample standard deviation? It's still 2 populations, and we're still trying to say whether or not they're the same or they're different or which one's bigger, but the data gives me sample standard deviation, so I need to run a different test. All right, so let's go back up, see if we can set up this whole problem. What's the claim? Well, the claim is that there is a difference in the scores. That is that mu sub 1 is not the same as mu sub 2. Hypotheses, that means that the alternate is that mu sub 1 is not the same as mu sub 2. The null would be that mu sub 1 is the same as mu sub 2. Effectively, mu sub 1 means doesn't matter which teacher, test scores are the same. Mu sub 2, it matters which teacher, test scores are different. Right? Our data, well, our data is, I've got all of this about teacher 1. My sample mean is 473. I got a sample standard deviation of 39.7. I got a sample size of 8. Oh wait, no, it's okay because we're supposed to assume the populations are normally distributed. So being smaller than 30 is okay. Right? Group 2, sample 2, I got an X bar of 459. I got a standard deviation, a sample standard deviation of 25.4. I got an N sub 2 of 18. And I'm supposed to test this all at an alpha level of 0.10. Right? Because I have sample standard deviations, I'm going to run a 2 sample t test. And so why a t-test? Because I have sample standard deviations. We run a z-test when we have populations. We run a t-test when we have samples. Stat, tests, 2 sample t-test. Right there, bring it up. I have statistics. Okay. Now this one actually is more logical, the order in which they ask you to put things in. X bar sub 1, mean for sample 1, 473. Standard deviation for sample 1, 39.7. Sample size, 8. Why did I type 5? 8. There we go. X bar 2, group 2, 459. Sample mean for group 2. Sample standard deviation, 24.5. Sample size, 18. There's more. What's the alternate is not equal to, so I make sure that's selected. I go down to, oh wow, what's this pooled, not pooled business? Okay. All right, so here's this weird thing. When the test is being conducted, the way that the standard deviation for the sampling distribution is calculated depends on whether or not the data should be pooled or not pooled. Now, the way we determine whether it is pooled or not pooled is based on this statement right here. If the variances are assumed to be equal, then we pool the data. If the variances are assumed to be not equal, we do not pool the data. Now, for this example right here, it says the variances, the population variances are not equal, so we'll select no. If, for whatever reason, it said the population variances were equal or assumed to be equal, we would select yes. Most of the time, it's no. Okay? So then I calculate. If I needed my standard test statistic, there it is at 2.899. What I need is my p-value. My p-value is, what is it? 0.016116. Well, actually, it should be 17 if I round correctly. Okay. I'm going to compare that p-value to my alpha. That p is way less than alpha. When p is less than alpha, we reject the null hypothesis. Remember, our claim was the alternate. So what does it mean when we reject the null and the claim is the alternate? Well, that means we have enough evidence to support the claim. So there is enough evidence to support the claim that the two groups have different mean test scores. Now, I don't know about you, but which teacher's better? I mean, this one's got a higher average, but also a lot more variability. This one's got a lower average, not by much, 14 points, but a smaller standard deviation, so less variability. Honestly, if I really cared about this problem, I would have written the claim about one of the teachers being better, having a higher test average than the other, and see if I could support that. Like if you think that teacher 1 is better, maybe the claim should have been that teacher 1's test scores are better than teacher 2's test scores. Where then our claim would be that mu1 is better than mu2, bigger, greater than mu2. But that's not how this problem is written. And so I work the problems as they're written because that's essentially what I'm told to do. All right, that brings us to the end of the first video. I'm going to stop this one here. We'll come back and in our second video, we'll take a look at 1, 2, more examples, and then we'll move on to section 9.3. I'll see you back here for part 2.